I'd like to say a few words about the objectives as well as the contents of the two courses on basic physics that we are going to go through. First of all, the overall objective of the courses is to provide an overview and a perspective of the basic concepts of elementary physics at the standard 11 and standard 12 levels. The first of these courses will consist of mechanics, heat, oscillations and waves, while the second will consist of electricity, magnetism, light and atomic physics. Now, which topics are we going to cover and why we are going to cover these topics requires a little bit of explanation. As I've said before, the two courses will basically deal with whatever physics you learn in standard 11 and standard 12 according to the CBSE syllabus. Now, the topics I've selected have been selected on the basis of the extent to which these basic concepts are involved and fundamental principles are involved in understanding the physics at this level. They therefore have very wide applicability, and these topics are also the topics that are conceptually the deepest and must therefore be understood if you want to understand physics itself, and you must understand it as clearly as possible. This is going to be the overall objective of these courses. Now, the important question that immediately arises is how much mathematics do you need to know? So what's the prerequisite in terms of mathematics? Well, for these courses, the prerequisite is going to be a familiarity with elementary mathematics at the standard 10 level, which you've all gone through. But I must immediately hasten to point out something very important. Standard 10 mathematics is necessary as a component to understand physics at the 11th and 12th standard levels, but it's not sufficient. It's not as if all the mathematics that you need to understand physics at standard 11 and 12 levels is covered in the standard 10 mathematics syllabus in a self-contained form. Not at all, by no means. And an early recognition of this fact will go a long way in avoiding frustration. First, I must explain why we need mathematics at all. Well, the language of physics happens to be essentially mathematical. To quote Galileo himself, the book of nature is written in the language of mathematics. Physics is a precise and logical subject, and it requires a language that has logic built into it. As Richard Feynman said, mathematics is language plus logic. So a certain degree of familiarity with elementary mathematics is therefore not only helpful, but also absolutely necessary for you to really understand physics and to appreciate the concepts and laws of physics at a basic level. Now, how much mathematics should you know? But mathematics itself is a very wide pasture. It varies in scope. It runs all the way from elementary arithmetic right up to the state-of-the-art research in mathematics. It's therefore natural that the following question arises in your mind. Exactly how much mathematics do I need to study physics and to understand physics? There can be no definite answer to this question. It depends on the level at which one wishes to understand physics. The problems that physics addresses actually require mathematics all the way from very elementary arithmetic right up to state-of-the-art research level mathematics. Now, there's a basic difficulty that arises immediately. In practical terms, and as far as the present courses are concerned, many topics that you handle in physics in standard 11 and 12 require mathematics at a level that's taught in standard 11 and 12 itself. So these things have to go side by side. We therefore have a situation in which you as a student will have to use mathematical tools that you have barely become familiar with or are not yet familiar with completely in order to understand the physics. Now, what's the resolution to this difficulty? Well, the problem is a threefold problem. The first part of the problem is that you have to take a physical situation described in qualitative terms, translate it into mathematical language, pose it as a precise mathematical problem. In step 2, you have to solve the mathematical problem using tools which you have just begun to learn. And in step 3, you have to retranslate the mathematical solution back into physical terms and interpret it in descriptive terms. Now, this three-step process is not trivial at all. It's not trivial even for professional physicists, and therefore it's not surprising that it's a very difficult and non-trivial task for a beginning student. But if you understand this and make allowances for it, it will go a long way in avoiding getting frustrated by the seemingly difficult nature of physics at this level. Now, what's the solution? Now, what's the concrete solution to this problem? It's that one has to turn this disadvantage into an advantage and not wait till all the mathematics is covered first, not at all. The trick is to turn the handicap to an advantage. We motivate the mathematics itself in terms of appropriate physical applications that require the mathematics concerned. The study of physics and the relevant mathematics can therefore and must therefore proceed side by side. Now, to give an example, a very, very good example of this strategy, I'll assume no prior knowledge of the calculus to start with in the first of the two courses. But you'll see that many of the terms and concepts of the calculus will gradually and increasingly appear in a very natural way as we go along in this course. Similarly, the mathematics of vectors, for instance, appears very naturally not only in mechanics but also in electricity and magnetism. You will see that the operational rules of many of these mathematical topics have a very natural interpretation in terms of physical applications. The important thing, therefore, is to avoid mental compartmentalization of the subjects and to imagine that anything that you say in words is physical, whereas anything that you write in equations or symbols is mathematical. This is not true. Both notions are erroneous. Cultivating a mental integration or synthesis of physics and the relevant mathematics at this level is therefore an important step on your road to understanding physics and to understanding mathematics as well. Okay. Now, to run through the topics that we are going to talk about, in the first course on mechanics, heat, oscillations and waves, we will look at first the nature of physical laws, then go on to the fundamental forces of nature, dimensional analysis and scaling, scalars and vectors, circular motion, kinematics versus dynamics, the laws of motion, conservation of momentum, conservation of energy, rotation about a fixed axis, conservation of angular momentum, the universal law of gravitation, Kepler's laws of planetary motion, gravitational potential energy, elastic behavior of solids, strain and elastic moduli, streamlined flow of fluids, heat, temperature and the ideal gas, change of state, thermal equilibrium and the laws of thermodynamics, degrees of freedom and the equipartition of energy, undamped and damped simple harmonic motion, wave motion, traveling waves and standing waves, and the superposition of waves. In the second course on electricity, magnetism, light and atomic physics, we will touch upon electric charges and Coulomb's law, the electric field, Gauss's law, electrostatic potential, the potential energy of a system of charges, the electric dipole, electric currents, Ohm's law and resistivity, magnetic field, motion of charged particles in magnetic and electric fields, the Biot-Savart law, Ampere's circuital law, magnetic dipoles, magnetism in materials, magnetic flux and Faraday's law of induction, the energy of electric and magnetic fields, the LCR series circuit, Maxwell's displacement current, the basic equations of electromagnetism, electromagnetic waves and electromagnetic spectrum, ray optics, the idea of a refractive index, and the laws of reflection and refraction. We will also go on to talk about a few topics in what's called modern physics, but is actually quite old by now. This has got to do with things like Young's double slit experiment and interference, the wave particle duality of light, the properties of photons, wave particle duality of matter, the Bohr model of the hydrogen atom, nuclear force and the binding energy of nuclei, neutrons and protons, and radioactive decay and the weak force. We will take a broad excursion through these topics, try to point out interrelationships between them, and try to see how they fit into our understanding of physics at a very basic level.